So we know that regression is a mathematical statistical way to use one or more variables to predict a particular outcome for a dependent variable. So we've got at least one independent variable, and if that's the case, then that's what we refer to as simple regression. But if we have more than one independent variable or more than one predictor, that is multiple regression. So let's go through just a couple examples beginning in your Green and Salkin book, lesson 34. There are a couple of pretty good examples I want to do from here. Let me make sure I can get that on the screen for you. So let's look at lesson 34, data file 1. In lesson 34, data file 1, the scenario shows up on page 286, the middle of the page, where it says one set of predictors. So with the simple regression, we had one predictor, period. Now we've got a set of predictors, meaning more than one, plural. So what we're going to have, the scenario is that we've got different measures of strength, and we've got an injury index. And we want to see if we can use measures of strength, or how well we can use measures of strength to predict the injury index. And instead of combining all these measures of strength together, we're going to leave them separately. For example, I want to know quad strength, glute strength, abdominal strength, arm strength, grip strength, they all go into predicting injury. So how do they work together? That's the multiple part of multiple regression. So if you look at the setup, the data view, you'll see a bunch of rows and columns, and the columns are variables. Some of those variables are predictors, some of those variables are the outcomes. Again, by the predictors, that's what I mean to label as independent variables. The outcomes are the dependent variables, and that'll come into play when we fill in some of those boxes that we're just about to see, that you know that we'll get when we come down some of these drop-down menus. So 1, 2, 3, 4, 5 different kinds of strength and a single injury index. I'm not concerned about age or the median index or whatever that stands for. I'm just concerned about the types of strength and the injury for right now. They use that data in another example that I'm probably not going to do unless you have a question you want me to, because that's not the other one I plan on. So we know we always start to analyze. Oh, I don't need to do any kind of a transformation or combining variables like we've done before. So that's what I mean by leaving these things separate, or as measures of separate strength. So we're going to go to analyze. If we want to do regression, we go to regression. And even though we have more than one predictor, it's still going to be linear regression. It's multiple linear regression, but it's still linear regression. So I'm going to click linear regression, and I'm going to have a window open up asking me to put some things in certain boxes. Now, as we said, the dependent variable is what we're trying to predict. That's the outcome. So we're trying to predict injury, or whatever we mean by injury index. And for the independent variable, and we saw the same box. So far, we've not done anything different than we've done in simple regression, but you may have noticed in simple regression the independent box is bigger. That's because it's possible that we can have more than one, which we have more than one now. With simple, we just had the one. So now we're going to put, all that we have in there. So I'm going to put everything from quads down through grips, and you can move these one at a time, or you can just select them all at once like I have, or whatever. So as long as you have the predictors for the independent variables. And I know SPSS is funny, and we've seen other examples. We'll see even more examples where this box may be labeled independent variable, it may be labeled something about grouping, or it may be labeled something like fixed factor. They all mean independent variables. I don't know why they use different. Well, I do. They use different names because the contexts are a little bit differently. So if we've got everything in the right box, I'm going to click Statistics, and the default options are Estimates and Model Fit, which may or may not mean anything to add. I don't think I've mentioned Model Fit. I think I've talked about estimates a little bit. But we also want to have confidence intervals. We want to have the R-squared box. we want descriptives, and we want part and partial correlations. So if you're watching this recorded, you can pause that or rewind it or whatever you need to, but in real time, it's estimates is defaulted to already. Confidence intervals you have to manually select. Model fits the default option already, and you have to also manually select R-squared change, descriptives, and part and partial correlations. And we'll see where those numbers go, and I'll be more specific about that in the second example I do in just a minute. For this example, all I really want to do is get to where we can produce the equation that predicts. So if I'm okay with that, I'm going to click Continue, and that'll get me back to that first drop-down box that came up. And I'm going to click OK, and that's going to give me an output window. It's going to give me an output window. Oh, that's underneath. There's my output window. Now, just a little bit of a sneak preview. Why can't I move that over? Well, if I can, I can't. That's okay. Oops. That's pretty, but don't want it. Okay. Notice I've got several tables that pop up. The first table is correlations. Now, my actual correlations are just this top third of it. And notice again my diagonals of 1. If you harken back to a million years ago when we first started talking about correlations back in the previous course, we talked about how there's always a diagonal of 1 because those 1s represent correlating some variable with itself. And of course something correlates with itself. Then you get the upper right triangle and you get the lower left triangle, which are mirror images of each other. So there's duplicate information here. We generally refer to the lower left triangle. So I can look at all kinds of correlations. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's about 15 correlations here. 15 ways we compare this data together. So those are the correlations, the R values. Some are positive, some are negative. Some are correlated positively, some are correlated negatively. Some are stronger than the other. And we can see that by looking at the middle third of the table. The significance, and again, notice my diagonal not of 1s this time, but just kind of nothings, just kind of blanks. And again, I'm looking at the lower left triangle because that gives me the same information as the upper right. But for example, the correlation between quads and injury, that correlation is negative 0.162. But the significance, the p-value, is 0.054, meaning it's not quite significant at the 0.05 level. It's almost there, but not quite so good. Everything else, it looks like, with the exception of grip and injury, is that the only one that's not significant? And I'm more concerned with how they correlate to injury because that's my predicted outcome. I can also see how they correlate with each other if you're following my mouse on the screen. But for example, abdominal strength and injury, P is equal to 0.01, and that's less than 0.05, so that's a significant correlation. The last part, the last third of that table is not particularly helpful. It just tells us that, hey, you got 100 of all these. Well, we knew that. We knew what the N was, but okay, that's fine. It tells us the N. The question was, does it all have to be the same size? Well, it kind of does because you've got all these. Well, yeah, good question. Yes, it kind of does because you're taking all these measures from the same people to produce the injury index in the same people. So generally, for this kind of analysis, generally you'll get the same size. You may have some missing data. And there are a couple ways to handle missing data, and I know I've pointed out a couple of times on those the boxes that pop up with the drop-down menus. It gives you some options about how to handle missing data. You can either throw them away or average them or whatever. There's 2 or 3 options there. Scrolling down in the model summary, a couple things that we want to pay attention to here are the R value and the R squared value, 0.426 and 0.182. If you're trying to follow along with the example write-up in the back of this lesson, then you'll see those numbers rounded off. You'll see the R value is 0.43, and 0.43 squared is about 0.18. And we talked about how the R squared is the indication of effect size. It has to do with things like how the variance in one variable is related to the variance, or accounts for the variance in the other variable. A couple of other things. Didn't mean to do that, but that's okay. A couple of other things are going to be important. Notice there's an ANOVA involved. And I'm looking at 5 and 94 degrees of freedom, respectively, and that F value is 4.18, and the P value is 0.002. That also comes into play in the write-up that you'll see in a few minutes. The main thing I wanted to get to, though, is down toward, why does it keep doing, what am I doing to take that picture? Under coefficients, and you see there are several things because of the options I clicked, and we'll get to these things at the end of the table in a little bit later when we talk about the write-ups. But mainly, the most important things in this whole whole output window are the numbers here, unstandardized coefficients. And that tells me that, let's see if I can get this on the screen or not. I don't know if I can. Okay. Never mind. We'll go back to here and do it. Okay. We're trying to predict injury index, right? So I'm going to say injury, and here's where I cannot write well with this. Let's see if I can do it this way. Ooh, this will let me. This is good. Injury can be predicted by saying, and look at my coefficients here, 0.628 times the quad strength minus 3.245 times the glute strength minus 0.563 times the abdominal strength minus 1.13 times the arm strength plus 0.794 times the grip strength. And pretend you can read my writing. At least this gives me an excuse for it being so lousy. And then plus, at the end of all this mess, is a constant of 260.393. So the bottom line, this is how we come up with the equation to predict. If you've got all these strength measures, we can predict an outcome or an injury index. Now, some of these variables are stronger and better predictors than others, and I'll emphasize that in the next example when I relate this back to a write-up. But for right now, the main thing, and I circled some things that we're going to go back and look at and talk about a little more, but this is the equation we come up with. So far, so good. Questions, thoughts, comments? Arm is 0.008. Now look at the B column. The arm strength coefficient is. Oh, okay. You're getting that from the correlation probably. No, don't get. It's not the correlation. It's the coefficient. That's in a different place of the output windows. So that might have been maybe that was something from the correlation or an earlier part of the table. But these are the variables and the constant at the end that we use for the equation. Okay. Any other questions? All right. Then let's look at one more example, and then let's couple this with a write-up. If you will go to stay in the same lesson Let's go to page 298, again, still green and silicon, 298, and exercise 1, which starts about 5 lines from the top and goes all the way through what's labeled as question number 5. Okay, what I'm going to do is we're going to call this up. I'm going to go through, I'm going to run the analysis, and again, it's just a very few clicks of the mouse to run the analysis. But then I've got to write-up, and this is in your D2L file, this newly posted. There's a D2L file with both the write-up and the output window that you're going to see, and highlighted where the numbers in the write-up come from in the output window. So I've tried to coordinate those. I can only get so much on the screen, so we'll see how well I can do that. So let me get rid of what we have. Well, I want it. Don't want to save it. Don't want to save it. There it is. Okay, so the scenario on page 298 is we're trying to predict an average score on a statistics exam. And the factors that we're taking into consideration, the predictors we're using are a math aptitude test, an English aptitude test, the student's English GPA, the student's math GPA, and all the other GPAs and all the other courses. So I've got, again, 1, 2, 3, 4, 5 predictors and one dependent variable. So if I go to Analyze, so let's produce the output window first. Analyze is, I'm going to go down to Regression. It's still linear regression. My dependent variable is not that. My dependent variable is the percent on the and you can't read all of it. There's a command. I'm not going to figure out how to do it, but you can read the rest of these variable names. But it's the average percent correct on a, I don't know if I clicked it down or something. Anyway, that's our dependent variable. The average correct on a stat exam. And the others are independent variables or predictors in this case. So I should have 5 of them over there. You can do it all at one time. Yeah, if you highlight on one, hold the shift down, and then click the other. And I think you can do it. If you don't want them all, if they're not all in the same block, I think you can use Control to pick them individually and move them over. Like you can skip some, go back and forth. So, want to do statistics, and again, I want to select the things that are not defaulted to. Defaulted selections, the confidence intervals, R-squared, descriptive, part and partial correlation. I probably click fewer boxes with this procedure than we've clicked on a lot of other ones. It's just, you get a lot more stuff, and the trick is knowing what to do with all that stuff, as we've been trying to figure out. So if I click continue, it's going to get me back to my other box where I put the variables in the right places. If I click OK, it's going to give me an output window. It's going to give me an output window. There's my output window. Now, I would suggest, and I've made this suggestion earlier, but it's another good time to emphasize it. I would suggest if you print any hard copies of this stuff, print them in landscape form, because it's, even when I put this into a document, I still put it in landscape. It still chops some columns off, but it chopped fewer columns off than if I hadn't done landscape. So when you keep in mind in the example I'm going to show you where I've put this output window in hard copy, not the output window, but, well, yeah, the output window. I have, sometimes the columns break from one page to the next. So I've got the same information. I'm not going to belabor the point so much on this one. I'm going to call up the document that I've scanned a PDF in for you. So again, all my descriptive statistics, you've got means and standard deviations of everything. All my correlations, again, notice my diagonal of 1. I'm particularly interested in the first column. I've got correlations of the predictors with the outcome or with the dependent variable. I've also got correlations of the predictors with the other predictors, which we'll talk about too. Again, my significant levels here, I've got of the correlations with the dependent variable, 1, 2, 3 of them are significant. Math aptitude, English aptitude, and math GPA. Okay, remember that because I'm going to come back to that in just a minute. 3 of these are significant. So if you've got a way, you might want to at least take note or circle these 3 numbers. The math aptitude score had a correlation of 0.484 with the statistics exam result. English was a lot lower in terms of correlation, but it's still significant. High school math GPA had a correlation of 0.229, but it's still significant. Hey, which do you think would be the best predictor? If you had to pick a single best predictor, which one would be the best predictor of the stat exam? It would indeed be math aptitude, because that has the strongest correlation, meaning not just the highest number here. You can't always tell from the correlation number itself because it depends on variability and all this other stuff. But because it has the lowest p-value, that might lead you to suspect that maybe that's the better predictor, as we'll see. It is, and you'll see that in a minute in a slightly different way. I got all my answers, 100 of everything. We do that. Also keep in mind that the R value is 0.519, or if the book was writing this up, and really if you're writing this up in your for your dissertation or something, you would write that as probably round that to 0.52. Except for the p-values, we generally round to 2 places. And R squared is 0.269. Again, that's the 0.519 squared. For the ANOVA part, I've got 5 and 94 degrees of freedom respectively. There's my F value. There's my P value. So somewhere we're going to see that F, again, just a sneak preview of coming attraction, spoiler alert, 5, 94 degrees of freedom. That F value is 6.922. And P is, again, we don't say P is equal to 0. P is less than 0.001. I did, but I can write it again. Five and 94 degrees of freedom, respectively. So the F value for those 5 and 94 degrees of freedom is equal to 6.922. P is less than 0.001. That's going to show up in the write-up in a minute. Okay. And down here for our prediction equation comes from this column for my unstandardized coefficient. It's unstandardized because we're not using z values. One of the examples in the Green and Salkin book uses z values, which I don't see a reason to, but they do. If you're using, well, I don't see a reason to in the example they did, let me put it that way. If you're using z values or standardized coefficients, that means you're turning everything into z's. Remember the 1.5 is 1.5 standard deviations above the mean. My coefficients are this column, the beta. And notice there's no constant here. If you look at that example in the book, it's just these numbers times the predictors. There's no constant at the end. you can see more directly what the better and worse coefficients are from the standardized coefficients, I'll say that. But in this case, so, we're trying to predict the stat exam score. So that stat exam score can be predicted from saying 0.116 times the math aptitude plus 0.049, I may not have room to write all this, but you'll see it, times the English aptitude, comes from here, and next minus 3.365 from the English GPA, and then I'll squeeze it in, plus 5.478 times that math GPA, minus, I think it'll let me right here, minus 9.702 times the other GPA. And I wanted to get to the end so I can remember to say, plus this constant, 6.745. I'll have this, I'll show it to you on the screen in actually legible notation here in just a minute. But look at a couple other things too. If I go to the end of this chart, and again on the printouts that you have, well, you can print them in hard copy, but on the PDF scans I have for you, this did wrap around to another page. But I'm concerned with the numbers in these two columns, and you'll see where they show up in just a minute. And I'm also concerned with the numbers in this column. According to this column, which is the only one that has a level of significance that we'd say, okay, that's significant? The math aptitude, which I scrolled off the side, but that's the p-value of the 0 here. And we said a minute ago, we said we expected that to be the strongest predictor. And that's what tells us that it is. So let's look at this in terms of a write-up. If I can remember what I did with it. Maybe I didn't open it. There it is. There it is. Okay, I can't go back and show you everything at the same time, but the things I've circled are the things I've highlighted here. And again, you have this in D2L. I have done things, like I say, a little bit differently than the book example did. For example, one thing I include, and I don't know why they don't do this, but I liked it, so I just put it in there because I can do that. The write-up example for multiple regression in Green and Southland does not give you the equation. Seems to me like that's kind of necessary. They give it to you in the simple regression example. So I include the equation. So I'll just insult your intelligence and read this to you. A multiple regression analysis was conducted to evaluate how well high school students selected aptitude scores and GPAs. They're all either aptitude scores or GPAs. I just kind of put them together. I had specific kinds of each one. To predict college success, success on the college statistics exam. The predictors were high school math and English aptitude tests. That's 2 of them right there. Math and English GPAs. That's 2 more, and then the GPAs and other courses. That's the other. So they're the 5. And then I have inserted the regression equation for predicting the college statistics exam score is, and this would be that sentence that I so messily wrote a minute ago. So 0.116, that was our coefficient for the math aptitude score. So 0.116 times whatever your math aptitude score is, plus, again, the coefficient for the English aptitude, which is 0.049, so that times the English aptitude. And then the rest of it, whatever the coefficient is, times the predictor. That number was negative 3.365 for the English GPA, 5.478 for the math GPA, negative 9.703 times the other GPA, and plus there's my constant at the end, 6.745. So I'm going to disagree a little bit with the book because I think that you know, they say all this stuff, but you have to kind of dig it out. If you actually wanted to really do a prediction, you'd have to dig to get this. So let's just say it up front. Now let's go down a little further, and I can go back to the output window if you'd like. Well, let me show you what else I've put on you. This I've given to you on the PDF, and here's this is okay. This is sideways. I told you I was going to do it in landscape. Go to the end. Those are those coefficient numbers we just read in the equation. So if everything I put in yellow on the write-up, I also put in yellow on the output, and this is a direct scan of the output window. Am I a nice guy or what? And then I talked about the ANOVA part. The linear combination of the predictors, and you can use those exact words if you want to. I don't care what the predictors are. You can say the linear combination of the predictors. The linear combination was significantly related. Now, the reason I can say significantly related is because this p-value. Remember those zeros I told you couldn't use a zero for p-value? You had to say p is less than 0.001. That's what it means by significantly related. If p was too large in the ANOVA part, you'd have to say it was not significantly related. But that's ANOVA, which we've done those, and we'll do some more of that too later. There's the F value for 5 and 94 degrees of freedom respectively. The F value was 6.92. I think I rounded that off. And then the sample multiple correlation coefficient was 0.52. I circled that. There it is. I circled it, but you know, my circlings disappear when I move things. So there's the 0.52. And then in a second, while I'm here, I'm going to go ahead and say that the R squared is 0.269. I'll probably round that off to 0.27. I did. So the sample multiple correlation coefficient was, again, you use the same language, the same words, 0.52, indicating that approximately 27%, that was the R squared number, of the variance of the exam index in the sample, so you have to tell exactly what it was, can be accounted for by the linear combination. You can use the word linear combination of the aptitude test and GPA measures. These are the predictors here. I just shortened all the predictors to say aptitude tests, and I should have said that should be plural. It should be a tests. And then to talk about what kind of matters more than other things, the last paragraph. Here's something else that I don't know if the example is this or not. I do this in APA style. In APA style, when you have a table, you have to refer to the table in the text before the table. So I say here, indices to indicate the relative strength of the individual predictors are indicated in Table 1, and I'm calling it Table 1. And again, you can use the same language as long as you change the dependent variable to whatever the heck you're talking about. Here we're talking about a statistics exam. That's our output. So whatever your output you put here. Well, not necessarily. That's just, we called this the, I don't know, did we call it index or did I just use it here? I'm not sure. I think we call it index. No, the word's not necessarily index all the time. You could probably say the question was, for the exercise that some of you do a write-up on, do you always call it index, or it was number of relapses? I think you could say number of relapses, or you can say the measure of relapses. There's nothing magic about the word index, no, which is, I think, what your question is. I think we called it index somewhere previously in the setup. Index is just it's a measure, it's a score. Yeah. I'm not necessarily using this as a technical term here, unless it's part of the test. If the test you're looking at as an output has the word indexes, yeah, you have to call it what it's called. Okay. Yeah, you could say the word relapse index for that right up that talks about that. Yeah, that's fine. Okay. So I refer to Table 1, and I just indicate in the sentence what I refer to as really kind of calling it the same thing that the title of the table is. And I'm trying to remember in APA, this might be Table 1 colon the title, I'm not sure. So there's some specific guidelines in APA that are a little bit funny, as we all know. All the bivariate correlations between the aptitude scores and GPAs and the statistics exam score index were positive. Let me show you where that is. Okay, that means all of these were positive correlations. The higher you scored on any one of these, the higher you scored on the exam. And again, I highlighted those in the write-up. I think. Actually, I didn't highlight all. I highlighted the .024 and the .484, which you'll see in a minute, because that's the high and the low. I wish I could point to two things at one time. Remember I said, remember 3 of these 5 were significant? I said this one, and this one. So I say that 3 of the 5 were significant. And again, I highlight those here where I say, and again, the page wraps a little bit, but so this, it actually works better kind of this way. This is the same as this is. These are just 2 more columns to it. So the 3 out of the 5, here's one of them, and one of them. I've highlighted the 3 that are significant, that are less than 0.05. And only the partial correlation between the math aptitude test score and the statistics exam score was successful. And that comes from toward the end of it anyway. I pointed that out to you to where I said, right here. Actually, it's almost the very end of it. But of this column at the end for the 0 order and partial correlations, the only significant you have here is, again, this has to be less than 0.05. So this is the one, and that's for the it's for math aptitude. I was trying to get everything on the same page at the same time, but I can't. But this is for math aptitude. As you've said early on, looks like that's the better predictor, or the best one. So. And what else I say? And toward the end here, there's not really anything magic to say. I just happen to throw in that the correlations between the stat exam scores and predictors range from 0.024 to 0.484. Here's the low, here's the high. Yep. And I could add a sentence that I decided not to because it's not, I don't think it's all that important. I could even say something like the correlations between the predictors range from whatever the low is to the high there is. Again, there's just, if you want to say it, fine. If you don't, it's no big deal. I'm more interested in the correlation with the outcome because that's what we're trying to predict. The comment was made, we can say the correlations between the predictors and the outcome, or yeah, you have to say, and if you say between something, you have to say between 2 things. Yeah, and I said range from a low of 0.024 to a high of 0.484. So they're all somewhere between there. And then for the table, note again at the very end of the output, I highlighted the columns of the zero order and partial correlations. These numbers that I'm pointing to here, the zero order column and the partial column, those are the same numbers that show up here. Notice it was that math aptitude that was significant. I give a little star and say, oh, by the way, don't forget this is significant. The comment was if you have some that are significant at the 0.05 level and some that are significant at the 0.01 level, do you separate those out and use like the 2-star for the really significant? You can. It doesn't matter. I mean, it's more detailed if you do it that way because, and where that's coming from is that on the SPSS output windows, when it flags significance, that's the way it'll flag it. It'll give you one little star for significant if P is less than 0.05, but if it's less than 0.01, it'll give you 2 little stars. And it'll say that. You can try. The blah, blah, blah part, yes, okay. The 27%. Oh, okay, yeah, I'm not finished. Okay, you're right, and yeah, there are a couple other things. Okay. The variable, and I'm looking at just the math aptitude score. Just the 0.484, because that was the one that was significant. That was the big one. 0.484 squared is 23%. 23% does not show up in your output window. You have to square the 484 and get that. So so what we're doing here at the end, we're identifying these are the real predictors. In this case, I have 1. Yeah, if you had more than 1, you could say these 2 accounted for, and then you could like say that all in one sentence too. Now, this is important. The part that's not. Yeah, I skipped over that. The part that's, it's the part at the very end where, yeah, you give the low and high correlations. If you give the correlations between predictors, no big deal. But yeah, let me go back and yeah, we see where the 484 came from. I started that. So 484 squared is how you get to 23. And again, you have to do that. Now, do you remember that 27% we came up with earlier? Well, if there's 27% altogether, and this is 23% of it, that leaves 4%. So the 27 that does come from the output window, minus the 23 that we just figured out, well, there's only 4% left that we haven't accounted for. Yeah, thanks for catching me to go back and get that one. No. Okay, the 0.484 comes from and go all the way to the end. Well, yeah, the zero order column. You said zero score, that threw me off. Yeah, the one that's significant. In this case, the 1 that's significant because my significance is 0.000. That corresponds. That's the significance level for the 0.484, which is the only one that is significant. So there's my 0.484. That squared, 0.484 times 0.484, is 0.23. Okay? Will what always be the same? Well, that's the one you use here. So yeah, because that's where it comes from. Yeah, the question was if we have multiples that are significant with the zero order. I would say if you got here's the way you can handle that. Dang, I got to do a lot of scrolling to get back and forth with these things. Let's say the 0.202 was significant. .484 is what, 23% we said? What's .202 squared? Can you be any less helpful? I mean, thank you so much. Okay, I'm on my slide rule here because I'm not trying to do this. It's like .4 or something like that. Actually, that's pretty close to it. Okay, that's .04. So that 23% plus 4%, that would account for 27%, which is about all of it. Yeah, what did you throw that in? Well, because they're not significant. Because they're not significant, it doesn't matter. Yeah, you could, but I'm not going to throw them in because they're kind of out there. They're not really that great a predictor as much as the. Focus on the ones that are significant, and yeah, okay, you can focus on just the one that's most significant. Yeah, because that's where the beef of it is, and that's what we're trying to find. If you got two that were really most significant, they're really close together, which I don't think is going to happen very often. I'm not sure it could happen at all, really. Then you might want to throw those together. I don't think that's going to be the case. Yes, my next to the last sentence is back up in the correlation part of the output window. Now the question was posed was what happens if you have a negative correlation? Do you say it's negative? Yeah, you do, because if you've got a negative correlation, like if you had a negative 0.2, you'd say, well, the correlations go from negative 0.2 to positive 0.484. There was another question, the 6.745. I don't know where is. Oh, the 6.745. That comes from. That's the. This is yeah, okay. That comes from the coefficient column, and that's the constant. The first thing in that coefficient column. There's the 6.745. The constant. And by constant, it means that's just a number that's standing on its own. It's not going to change. That's why at the end of the sentence you add the constant. That's just the constant number that you add to all those other things that you multiply to get there. It was right in the equation. Right here. If that's the one you're writing up, yes. I'm not going to specify that because not everybody's writing up the same one. Now, in your write-up, you can write up, you can write up exercise 2 that was the homework problem, or you can't write up this one because I've already done that for you. You can't write up the first example we did that's already done for you. There are a couple of other examples if you want to try something new, and again, I'll go over the homework here in a minute or a little bit next time. The Whit and Whit book has a little bit of this in here. I don't like the examples out of the Whit and Whit book to write up because their numbers are so small because they're writing their book to crank things out manually, and I'm certainly too lazy to do that. So therefore, their examples are they're not really as good examples as the Ingredient Alchemy book comes from. So I suspect most of you would write up the second one. Other questions, thoughts? Good. Okay, good. So we're okay with multiple regression, at least as far as we are now. Maybe. Okay.